going to start recording. That's right. You shared your screen. Good. Okay, brilliant. So welcome everybody. Hi. This is we're delighted that Julius has agreed to give a talk. This is the second seminar of this academic year. So we're really delighted that we're able to talk, and Julius will be telling us about bootstrapability for one-dimensional defect conformal field theories. So over to you.
Thank you. Thank you very much for that kind introduction. Thank you for the kind invitation. So I'd like to start by thanking the organizers for giving me the opportunity to talk, to present my work. So today I will be talking about bootstrability for 1D CFT. Bootstrability is our attempt to try to combine the techniques of integrability with conformal bootstrap to see where this kind of idea goes. I'll be presenting mainly results of this paper, which we wrote with David Grabner and Kolya Gromov almost 2 years ago, and an earlier paper which we wrote with Andrea Cavaglia, Kolya Gromov and Michelangelo Preti earlier this year, a few months ago. So let's get started. Everything is in sync. All right. So one can ask the question what it means to solve a conformal field theory, and usually solving the conformal field theory boils down to understanding having complete control over what's called the CFT data at any values of the parameters of the CFT itself. So in practice, this means we know the spectrum and structure constants of the conformal field theory non-perturbatively for any value of the parameters of the CFT. In general, past experience over many years has shown that this is quite a hard problem, and in general, it's really hard to solve the CFT. So one can ask, okay, is there some way to make our life a bit easier? And it turns out that for some special conformal field theories, for example, 4D n equals 4 supersymmetric Yang-Mills in the large n limit, so in the limit where the rank of the gauge group goes to infinity, there is there's an emergent structure called integrability, which makes life much easier and actually allows one to calculate the planar spectrum of the theory. So integrability was first seen in a very important paper of Minahan and Zariambo, and then there was almost 20 years of work towards the spectral problem in planar n equals 4 Yang-Mills, and it culminated in some sense with the writing down of the quantum spectral curve. And the quantum spectral curve was able to, in principle at least, give you access to the entire planar spectrum of n equals 4 Yang-Mills for any values of the parameter of the theory, which is the Hooft coupling. So in the first, let's say, first half of the talk, I will try to review the quantum spectral curve construction, give you some idea of the flavor of this construction for n equals 4 Yang-Mills, and then I will specialize a bit more into more bootstrapability kind of into those kind of topics. All right. So let's start with integrability for the spectrum of super Yang-Mills, n equals 4 super Yang-Mills. So let's consider operators defined in the following way. We have an operator which is a single trace of L scalars in n equals 4 Yang-Mills. So I should remind you that there are so L real scalars. So there are 6 real scalars in n equals 4 Yang-Mills theory. So we are considering length L operator, which is a trace of L scalars, and each of the scalars can be 1 out of 6 flavors if you want. Now, in general, of course, if you compute, and I here is just a generalized index, which is just a generalized index. And in general, if you want to just calculate the expectation value of OI, OJ, for example, then the expectation value obviously diverges. And in fact, we have a whole mixing matrix full of possible correlators between different choices for the scalars of size 6L to the power 6L. which we would have to compute if we want to understand how to renormalize these operators. So if you want to renormalize operators, these scalar operators, what you do is you construct this 6L by 6L mixing matrix, and each of them involves so each matrix element is a Feynman integral which you want to calculate, and then you want to diagonalize the matrix. So in general, this is quite a cumbersome process. So you want to diagonalize this mixing matrix, and then finally what you get is that the scaling dimension of your renormalized operators is actually corrected, and it picks up some quantum corrections which are given by the eigenvalues of your mixing matrix, and they are called the anomalous dimensions. So this is what we want to do. Of course, in practice, 6L by 6L matrix is really hard to diagonalize, even if you have a computer. But the remarkable thing which Minahan and Zaremba in 2002 were able to show is that the mixing matrix of a single trace of L scalars n in n equals 4 super Yang-Mills actually corresponds to the Hamiltonian of a closed length L SO6 integrable spin chain. So this means actually that the problem of finding anomalous dimensions, at least at one loop, I did not write here, but this is only at one loop. Yes. So this means at least at one loop that the problem of finding the anomalous dimensions of these kind of operators in n equals 4 super Yang-Mills just boils down to finding the energy spectrum of an integrable spin chain, which means actually now techniques of integrability can become useful for us. And this is already very good because integrability makes life much easier, as we will see. So to illustrate this, let me start with actually just the SU2 spin chain. So instead of having 6 real scalars, I can restrict to 2 complex scalars in the theory. So phi1 plus I phi2, I call that X, and phi5 plus I phi6, I call that Z. Now, this actually is a closed sector of the theory, and the spin chain Hamiltonian, or the mixing matrix for the SU2 sector at one loop can be written down right here. So this is your spin chain Hamiltonian. We have a sum over sites going from 1 to L. At each site, I have an identity operator which does nothing, and I have a permutation operator which flips the spin at each site, essentially. So in this picture, we have a correspondence between, let's say, some single trace operator made of X's and Z's, and some configuration of spins. In order to see how this works, let's consider the Hamiltonian in more detail. So suppose, let's consider the Hamiltonian which we had. It's clear that if we act with our Hamiltonian on a state with all spins down, then identity and permutation do the same thing. So then if you act with it, identity minus permutation just gives you 0. And this is a candidate for a ground state. So all spins down can be a ground state. Then you might want to ask the question, okay, how do I get excited states? One thought could be that, okay, I can have all spins down and I flip one of the spins up. But then immediately you see that if you act with the Hamiltonian on this, what it's going to do is it's just going to move one spin here. I mean, it's going to give you 2 things, one with the spin here, one with the spin here, but that's not really an eigenstate. So actually, the way you want to construct eigenstates of this Hamiltonian is actually by considering states which look like this, where I have spin up. So I have all spins down except the ith spin is looking up. And then I do a sum. So I have a phase factor here, and then I have a sum over all of the sides of the chain. Now, these states actually are eigenstates of the Hamiltonian, and they have some energy. And they have some energy which is given here, where P1 is the same thing that we had here. So in order to introduce some notation, psi1 is called a magnon, and this P1 here can be thought of as a momentum associated with the magnon. It's called a magnon because you can think about this as actually a kind of magnon moving through the chain. All right, so now we also need to impose a quantization condition, which basically means that if I take the magnon all around the chain, I should get back 1, and the way that is done is just by imposing that e to the I pi1l, ip1l is equal to. Okay. So in general, states are represented by multi-magnon states. So if you want to create a map between single trace operators, you want to create a map between them and multi-magnon states. And these states in general are n1 spin-ups in a sea of spin-downs. And in this case, the same quantization condition which we had, which is if I take one magnon and take it all around the chain, I should get back one. This obviously gets a bit modified because it also hits the other magnons. But then you can write down the quantization condition as a set of Bethe-Ansatz equations, where I've introduced just for the notation to be a bit simpler, u, which is the spectral parameter, and this is basically related to the magnon momentum. So you have some Bethe-Ansatz equations, and you can solve these equations to find your Bethe roots, which will correspond to the magnon momenta initially. And then once you have your Bethe roots, you can actually reconstruct the one loop. So the energy of the spin chain or your one loop anomalous dimension by just plugging into this formula. Okay. So this is how this construction works. Very good. So so this is how, sorry, let me just go back. So this is how the Bethe-Ansatz construction works for the sp2 spin chain. Now, bear with me for a moment, because I'm going to introduce just some notation which might not make too much sense. Right now, it just looks like I'm repackaging, but it's useful. So what one can do is one can collect all the Bethe roots into a polynomial known as the Baxter polynomial, and let's call it Q1. Right. So I just took all of the Bethe roots which I had before, and then I collected them into a polynomial called the Baxter polynomial. And I also noticed that the asymptotics of this polynomial goes as u to the power n1, where n1 is, I remind you, the number of spin-ups. Now, of course, I can rewrite the Bethe-Ansatz equations using the Baxter polynomial by introducing another notation, q theta equals u to the L, and another piece of notation that plus or minus basically just means a shift of the spectral parameter by plus or minus half I, plus or minus I, or plus or minus a times I over 2. So at the moment, this just looks like I've just rewritten something, but it's actually quite useful. The important thing is that these Baxter polynomials, they actually solve a Baxter equation, which is for the sp2 spin chain. It is an order 2 finite difference equation given over here, where t of u is just a polynomial which is fixed by self-consistency. The cool part is that the Baxter equation basically behaves as the analog of the Schrodinger equation for this sp2 spin chain. And in continuing the analogy, the Baxter polynomial, which we wrote down just now, Q1, is the analog of the wave function. So what this, if you allow yourself to believe this analogy, then also, so in this analogy, again, the charges of the state are in the asymptotics of the Baxter polynomial, similar to this WKB stuff, right? So as I showed in the previous slide, my Q1 goes as u to the n1. So that sort of analogy is also there here. Okay, so very good. What does this mean? Before I tell you what it means, I should also point out another thing which I didn't emphasize earlier, was that there was actually an ambiguity regarding the choice of the vacuum. I chose as a vacuum all spins down, but I could have equally chosen all spins to be up, because Hamiltonian acting on all spins up will also give 0. Suppose, let's say I had made that choice. If I had made that choice, then a state which was n spin-ups in a spin-down vacuum now actually corresponds to a state with L minus n1 spin-down excitations in a spin-up vacuum. Now, obviously, these two, and this state will actually be associated with another Baxter polynomial, which has the asymptotics u to the n2 or u to the L minus n1. Of course, both of these pictures should be completely equivalent, and they should describe the same state. And indeed, Q2 is just a second linearly independent solution of the second order Baxter equation, which we just wrote down. So that's very good. Now, the fact that Q1 and Q2 are actually linearly independent would mean that their Wronskian should be non-zero. And that means that actually I can write some kind of a Wronskian relation between Q1 and Q2. Of course, these are difference equations, so I have to do, instead of function and derivative, you have just shifts in the spectral parameter. But then the point is that there exists such a Wronskian relation. And so yeah, that's one thing to note. And the second thing to note is that actually one can kind of derive the Baxter equation just by considering some trivial determinant, some trivial determinant of Q1 and Q2. And then actually one can use this to also fix the form of Q12, for example. So that's very good. The reason I said all of this is because basically, if we reverse the logic which we started with, we get the logic of the quantum spectral curve. So what did we do till now? We said, okay, we start with the Bethe-Ansatz equations. We find that there are Q1 and Q2. Q1 and Q2 are solutions of the Bethe-Ansatz equations. And then we see that, okay, there are some QQ relations, there is a Baxter equation, etc., etc., etc. What we could have done, or the logic at least of the QSC, is you start with a QQ system or a set of QQ relations. Alternatively, you start with a set of QQ relations. You can derive a Baxter equation from them, but you don't have to. So you start with a set of QQ relations, impose the asymptotics of Q1 and Q2, impose the polynomiality assumption on T, Q1 and Q2. And from here, you can actually derive the Bethe-Ansatz equation. So this reverse logic is basically the main idea of the quantum spectral curve, the point that just the QQ system with the asymptotics and polynomiality conditions are completely equivalent to the Bethe-Ansatz. This is actually quite productive for us because the Bethe-Ansatz, of course, at one loop, it's nice. And for the SU2 sector, it's nice, but then as you include more and more operators, you get nested Bethe-Ansatz equations, and solving them really becomes a pain. Also, you have at more loops, you have spin chains which don't have local interactions. So in general, it's nice to have a way, at least in principle, of bypassing it. And that's what the quantum spectral curve provides. 1 sec, let me check. Okay, good. I'm doing good with time. All right. So now the point is that we aren't in a SU2 spin chain. We actually, the symmetry group of n equals 4 is PSU22/4. So instead of 2 Baxter polynomials, we would have 2 to the power 8 Baxter polynomials, and these polynomials would have up to 4 indices. There would be more of these Wronskian type relations which are described, called bosonic and fermionic dualities. Furthermore, there are also some Hodge duality relations, and all of this together are QQ relations, or form what's called the QQ system. Luckily, because of the QQ relations, only 8 of these Baxter polynomials, along with the QQ relations, can be used to obtain all 2 to the power 8 of them, which is quite good. And as I mentioned before, the asymptotics of the PA and QI contain all the charges of a state which are interested in. Another thing to mention is that we are not dealing with spin chains, but with ADS CFT. And so Baxter polynomials are no longer polynomials anymore. They are rather what are called Q functions. And this polynomiality assumption which we had cannot be used anymore. They have to be replaced by an analyticity assumption. And for at least planar n equals, so for ADS5 CFT4, the analyticity assumption is quite simple, that the 4 Q functions PA, P1, P2, P3, P4 have just a small branch cut between -2G and 2G, where I haven't mentioned this earlier. So G is equal to just square root of lambda over 4 pi, where lambda is the Hooft coupling. And the 4 Q functions have a long cut between -2G and 2G. So this is the review of the quantum spectral curve construction. And using this construction, one can, in principle at least, find the entire planar spectrum of n equals 4 super Yang-Mills non-perturbatively. Great. So now we can go back to almost the motivation slide and just add the word planar. Okay, so suppose I want to find planar CFT data. What do I need? Suppose I want to solve planar n equals 4 Yang-Mills. In principle, now I know the planar spectrum, which is really good. I still have no idea about the structure constants yet. Well, I shouldn't say that because actually there have been recently a lot of progress in this direction. But okay, for the purposes of the story, let's just say we don't know we don't know enough at least. And the thing is that if you restrict to the planar theory, we still need some non-planar input. Because if you try to consider 4-point function even of 4 scalars in the planar limit, you will still need some non-planar input. Some double trace terms still contribute in the OPE, for example. So the problem is still hard, and it's still a bit annoying because now we have this extra thing here which we don't have full control over. So then the next thing we can ask is, okay, is there a way to kind of either bypass the step or not have to think about the step? And it turns out that there is a setup. So if we consider line defects within n equals 4 super Yang-Mills, actually it is possible to simplify the problem further and actually make some progress, as I will describe in the next step. But before I do that, and so the simplification is achieved by studying a line defect in n equals 4 Yang-Mills. But before I describe the line defect in further, I need to make a small detour and talk about the cusp-Wilson line, and then I will slowly get on to the line defect.
Julius, sorry, can I ask a question? You say your point 3, where you need some non-planar input.
Yes.
In this hexagon story, are you saying that they also technically...
yeah, good.
Yeah, yes. So this hexagon approach, do they also have the problem that they need some non-planar input?
I'm not totally sure. No, my statement here was just that if you consider like the 4-point function of 420 bar operators, 20 dash operators in n equals 4 Yang-Mills, and then you write down the OPE, then all the operators that contribute to the OP, you have a lot of planar operators like your Konishi and friends, but then there are also double trace operators with the same kind of quantum numbers, which will also contribite to the OP. So that's what I mean. So we don't. So QSC, at least right now, cannot tell you anything about their scaling dimension. That was my statement. I'm not very sure about hexagons. I think hexagons they do one structure constant at a time. So maybe not. Maybe they don't see this problem, but I'm not sure.
Maybe related. So in the before here, so introduction part that the integrability story that is for planar sector. Or
yes.
Okay.
Integrability is only planar. Yes.
And that would mean L fixed and N goes to infinity.
That would mean that you keep the product G square Ym times N. You keep that fixed. Take G square Ym to 0. So take G Yang-Mills to 0 and N to infinity.
And there was also another parameter like a length of a spin chain that was also fixed.
No. So
that kind of
that's fine. Actually, so one of the things that QSC was able to solve was that we can, in principle, we know the dimension for any length. So before it was actually in the earlier days, only like almost infinite length was the only thing which was understood well. But so solving finite length is also non-trivial, and they managed to do it with the QSC. I mean, they did it with TBA, etc., but QSC is a nice way to see it. Yeah.
Thank you.
Okay. All right. So small detour, and I want to introduce this observable, which is just a cusped Wilson line n equals 4 Yang-Mills with some scalar insertions. So I have here a Maldacena-Wilson line. So like it's coming from minus infinity to this point. And because it's a Maldacena-Wilson line, I don't just have the gauge field. I also include a coupling to the scalars. And this is just notation to show that I've picked one out of the 6 scalars to be coupled along this ray. And then I have another Wilson ray, and along this ray I couple I couple a different scalar so that in this space of scalars, the two scalars make an angle of cos theta. Also, there is an angle phi, which is the cusp angle, the physical cusp angle, we can say. So it's the angle that the two Wilson rays make with each other. And at this point, I make some scalar insertion, some operator insertions. Now, this observable in general, it diverges, and the divergence is controlled by, in the case of if you have some scalar insertions, it's controlled by the scaling dimension of the cusp Wilson line with insertions. In case you make no insertions, it is just controlled by the cusp anomalous dimension. Now, for this setup, if you take these two angles, theta and phi, to 0, so then you basically bring this thing down, then you land on the half BPS Maldacena-Wilson line, which is a one-dimensional defect CFT. I will get to it. So that's the defect CFT which I want to study further, but I had to introduce this before I do that because the integrability stuff was developed here. All right, so let me give you just a small survey of the results. So let's restrict to scalar insertions at the cusp for concreteness. So we can have two types of scalar insertions. The first type would be scalars which are orthogonal to the scalars that couple to the line. So as I mentioned, these two directions are the directions of scalars coupled to the line. So I have a R4. I have R4 size space of insertions which are orthogonal to these two scalars, and any such insertion is an orthogonal insertion. So for particular type of orthogonal insertions, the thermodynamic Bethe ansatz was written down by Nadav and also by Maldacena-Correa-Sever in 2012. And also after that, there was a QSC description for the same setup developed by Kolya and Fyodor. So this is for orthogonal insertions. Also, another type of insertion you can have are called parallel insertions. So these insertions are insertions which are in the span of the scalars that couple to the Wilson line, the Wilson lines. Okay, so there's an R2 size space there. Now, such insertions in a special limit called the ladder's limit, they were realized to be described by the same quantum spectral curve, which was developed for orthogonal insertions in this paper of Andrea, Kolya, and Fyodor. And for general values of theta and phi, it was extended by David, Kolya, and me. So we managed to extend. The point of this slide is to tell you that the QSC description, which was developed for orthogonal insertions on the Wilson line, was extended to parallel insertions as well. And this is important, as we will see in a few slides' time. All right. So as I said, if we take phi and theta to 0 in our Wilson line, then we end up on the half BPS Maldacena-Wilson line in n = 4 Yang-Mills. This is just your usual Wilson line, but then also I include coupling to one of the 6 scalars. I denote it by phi parallel over here. Now, this Wilson line, operator insertions on this Wilson line, you can take expectation value of this Wilson line with various operators inserted at different points on the line, and this expectation value behaves exactly like the expectation value of a CFT. So you can consider the Wilson line to be a one-dimensional defect CFT. Yes, so you can consider it to be a one-dimensional defect CFT. And for this defect CFT, let's consider the kind of symmetry group, right? So the conformal group, of course, is broken down. The 4D conformal group is broken down into the 1D conformal group along the line times 3-dimensional rotations around the line. The SO6 space of scalars which we had, now because I've chosen a particular direction in scalar space, so now that's broken down to an SO5 defect R symmetry. So in general, PSU22/4 becomes OSP4/4 for this defect CFT. Furthermore, we can consider some more operators in this defect CFT. So there are many half BPS multiplets, but for our discussion, there are 2 important ones. the so-called B1 multiplet, which contains the 5 orthogonal scalars. So it contains the 5 scalars that don't couple to the line. So these have protected scaling dimension of 1. Then also you can make some symmetric combination of them, and they belong to the B2 multiplet, they have protected scaling dimension delta equals 2. There are also fermions and other things in these multiplets as well. But in particular interest to us is the long multiplets. Now, the long multiplets are those which don't have protected scaling dimension. So these insertions, so these are operator insertions on the Wilson line, which are not protected. So we don't know non-perturbatively. In principle, we don't know non-perturbatively what their scaling dimension would look like. Or said in another way, we need to figure out what the scaling dimension looks like. So kind of insertions we can have actually include an insertion of phi parallel on the Wilson line. So exactly the same scalar which couples to the line. So this would be an operator which has engineering dimension equal to 1, for example. Or we can have also any kind of neutral combination of the orthogonal scalars or just more parallel scalars. And then also this will have some engineering dimension. But the main point is that for the long operators, the dimension does obtain quantum corrections. Okay, so let's think a bit more about how we can label, for example, these long operators. It turns out that we can label these long operators using the same oscillator technology which was developed for n equals 4 super Yang-Mills by various papers of these authors. So the point is that we associate with any operator 4 fermionic oscillators and 4 bosonic oscillators, and then there is some dictionary which tells you how to translate between oscillator numbers and quantum fields. Okay, so it turns out that for singlet operators in the defect CFT, so let me explain this. So these are long operators which don't have any defect R charge and don't have any also indices associated with the SO3 symmetry you have around the line. So these are operators with no indices at all. These are long operators, so they are not protected. So such operators, i.e., let me go back a slide. So they are operators. So all of these operators are singlets. You have this one. You have this one. You can also construct some with phi parallel cube, for example. You can have also covariant derivatives in the direction of the line, etc., etc. So for singlet operators in the defect CFT, we can actually label them using the same oscillator technology of n equals 4 in the following way. So in this notation, delta naught, as I said, is the engineering dimension. Twist T is something which we call twist. And well, I've put twist in quotes because twist actually should mean should have something to do with spin, but we don't really have spin in this 1D line here, but it's still similar. And also delta naught minus T gives roughly the number of covariant derivatives in the direction of the Wilson line. So what this means is that an operator of scaling dimension delta naught and twist T roughly looks something like this. You have delta naught minus T number of covariant derivatives, and you have phi to the power delta naught. Okay, so these are the kind of singlet operators in this defect CFT, and this is how one can organize them. All right, so again, just some notes about some more about these operators. In the case that the twist is equal to delta, this means that I have twist minus delta as the number of derivatives. So if twist is equal to delta, I have no derivatives. So these are all the operators which I can construct using the letters phi parallel and phi orthogonal. And it turns out actually that the one loop mixing matrix for these operators is integrable, and it was written down in this paper. For delta and twist equal to 1, this just corresponds to a single insertion of phi parallel on the Wilson line, and this was shown by us to be accessible by the QSC. For twist equals 2, this corresponds to operators with maximal number of derivatives. And this also is accessible by the QSC, and this is something which I worked out. And with Andrea Cavaglia and Michelangelo, we were able to extend the same construction for any twist, i.e., we were able to bring the entire singlet spectrum under the same quantum spectral curve. I mean, we were able to show that the entire singlet spectrum is described by the same quantum spectral curve. All right, so let me actually show you what the QSC for the defect CFT is. So as I mentioned a few slides ago, for the QSC, we have 4 P functions and 4 Q functions, and using this, you can construct all the other ones which you need. So asymptotically, they look like this. And as you can see, the charges of the state. So because I'm looking at singlet operators, the only charge which I have is delta, and delta is sitting here in the asymptotics of Q1, Q2, Q3, Q4. Now that I have the P and P's and the Q functions, I can also do something which I did earlier, which is kind of derive a Baxter equation by considering some kind of trivial determinant. And so in particular, for this case, the trivial determinant one needs to consider is this rather ugly looking determinant of P1, P2, P3, and P4. But this, you can show that if you start with this trivial determinant, you can derive a Baxter-like equation, a 4th order Baxter-like equation, a 4th order Baxter-like equation. So, okay, so we did that. And then basically what I want to show you is, so we can do this. And for example, we can derive a tree-level Baxter equation for the twist 2 operators. So this Baxter equation has some coefficient multiplied by Qi u plus 2i, Qi u plus I, Qi u minus 2i, Qi u minus I, and Qi u. So basically, it's a 4th order finite difference equation. And it is a finite difference equation for a function Qi, which is nothing but the Q's which I showed you on the previous slide, just divided by square root of u. These coefficients here, they depend only on delta naught, which is your engineering dimension, and C is just some parameter of one of the P functions at tree level. Now this Baxter, so this is the Baxter equation, and 2 of the 4 solutions. So it's a 4th order finite difference equation, and 2 out of the 4 solutions of this finite difference equation are actually polynomial, and that's because at weak coupling, basically we reduce to a highest weight spin chain. So and that's why we have 2 polynomial solutions. Very good. So now that we have the Baxter equation, we actually have an algorithm which we can use to map out all twist 2 states. So how do we do this? We start by fixing the value of the engineering dimension. So we fix delta naught. Then we impose our 2 polynomial solutions. I've written these 2 in a very non-polynomial way, but if you look at it, you see here, this is actually a polynomial. So we impose that there are 2 polynomial solutions with some coefficients, undetermined coefficients, A2, A3, etc., B2, B3, etc. And then by self-consistency, you can fix the values of AIs, BIs, and C. Now it turns out that it could be that for a fixed value of delta, there are multiple sets of AI, BI, and C which solve the Baxter equation. But actually, all that means is that this means that there are multiple states which become degenerate at weak coupling. Which is really good, because just by solving this Baxter equation, I'm actually solving both the counting of states problem for a given engineering dimension and the mixin problem for a given engineering dimension. I'm solving both of these for free. Anyway, so now I've got my 2 polynomial solutions for my Baxter equation. Using those 2 solutions, using those 2 solutions, you can then find the 2 non-polynomial solutions. Now, these non-polynomial solutions are actually quite complicated functions with an infinite number of poles below the real axis, etc., etc. But there's a well understood way of solving them. So you can find Q3 and Q4. Then again, there's well understood ways of starting with your tree level Q functions and then generating perturbative data using a method developed in this paper. And then once you have enough perturbative data, you can actually start a numerical solution of the quantum spectral curve using the numerical algorithm developed in this paper. And in general, you can map out the entire twist. In principle, sorry, you can map out the twist to the entire. You can map out all twist to states in this defect CFT. In fact, we can do. Yeah. Okay. In fact, we can. Yes,
Julius,
yes.
Can I ask another question? Sorry.
Yes, please.
At this point, you've made an assumption that you don't have any cuts. So your polynomial, as if you were doing a generalized Heisenberg. You're not
Yes,
anymore
yes.
in Joukowsky variables.
Yes, because I'm at tree level. So G is 0.
You're still at tree level. Okay.
Yes, yes. This is at tree level. Until here, I'm at tree level.
Yeah.
Then
okay.
I generate perturbative data, etc., etc. Yes.
But then you will go back to the Joukowsky parameterization. You'll introduce the cuts. Okay.
Yes. So, I mean, when I generate perturbative data, they are still in terms of these functions with a lot of poles, these eta functions, they're called in these papers. And then when you start the numerical algorithm, then you reintroduce the cut spaces.
Okay, I see. Thank you.
Okay, so we can not just do twist 2 states, but we can basically extract the entire, in principle, at least entire singlet spectrum. So that's quite cool. Okay, so I should plan a bit. How much time do I have left? Sorry.
About 18 minutes, 18.
Oh, perfect. Good. Yeah. Okay, so that should be good. Nice. So then, yeah, so we have the entire singlet spectrum. So let me explain this plot a bit. So here on this axis, we have G, which is just square root of Hooft coupling over 4 pi. On y-axis, we have delta for different states. This state was the state corresponding to a single insertion of phi parallel, which we obtained with David and Kolya. For delta is equal to 2, all the states are twist 2 states, so I was able to obtain them. And also for delta is equal to 3, we have for delta is equal to 3, we have twist 2 states and twist 3 states. There are 6 of them, so they are over here. I should point out that at strong coupling, there's a counting of operators available, which was done by Carlo Meneghelli and collaborators, and at least these many states are complete at strong coupling. At weak coupling, the first 3 levels are complete, and at delta naught equals 4, we managed to find 19 states, but then there's a possibility that it is incomplete. So that's something which we need to debug still. But in principle, we should have access to the entire spectrum. It's just a matter of relaxing some assumptions in the Baxter equation to find missing states, for example. So yes, so this is the entire spectral plot which we have. So great. So now we can go back again to what we started off with. So now I have a planar 1D defect conformal CFT data. So to solve a planar 1D defect conformal field theory, one needs the planar spectrum, which I just showed you on the previous slide. One also obviously still doesn't know structure constants, but the good part is that we don't need. So these sneaky double trace terms which were going to bother us earlier, they don't exist anymore. So it's still a hard problem, but it is more tractable. That's something that makes us happy. All right. So yeah, okay. So now we move on from the spectrum to the structure constants. And in order to do this, let's consider, as was done by these authors, a 4-point function of 4 orthogonal insertions on the Wilson line. So you have your Wilson line, and then you make 4 orthogonal insertions on it. Of course, by conformal field theory, this can be just reduced to a function, to some undetermined function of the cross ratio. In one dimension, I should mention that there's only one cross ratio because the 2 cross ratios are chi and 1 minus chi. So it's just a function of chi here. But then what Meneghelli, Liendo, and Mitev were able to show, I mean, they were able to use some constraints for superconformal symmetry, and they were able to write this function actually like this, which is doesn't look very much more simplifying at first, but basically if you write it like this, then you can do an OP which respects superconformal symmetry, so it's very useful. So yes, this function a of x can be written in terms of this term, where w is just the expectation value of the half BPS circle, which is known from localization, And D again is some known differential operator. So they were able to write this A in terms of this function. So now F is your undetermined function, is the undetermined function of your cross ratio. Also, they were able to show that the OP coefficient for the B2 multiplet, which will show up when we do the OP, when we write this in terms of the OP, we will also get some contribution from the B2 multiplet. So they were able to show that the OP coefficient of the B2 multiplet actually can just be obtained from this localization result. So that's actually very good. So yeah, so let me show you the OP. So you can write f of chi. You can do the operator product expansion, and then you have a number of terms. The first term is fine; it's just chi. The second term is the contribution of the B2 multiplet, and as I mentioned before, the OP coefficient. They were able to show the OP coefficient is known due to their work. They also managed to calculate the conformal blocks for this multiplet. And the third term which enters this OP are the long operators, which are singlets of the defect. So long singlet operators, and these are precisely the operators for which we managed to get the entire spectrum in principle. So for those operators, we have a sum over all of the operators. We have a sum over the spectrum. The spectrum in principle is known due to what I explained previously, and also Lee and Domenech managed to figure out the conformal blocks. So actually, the only unknowns in this entire in this equation is the OP coefficient or structure constants of the long operators. So that's very good. So then what one can do is one can impose crossing symmetry. We say that, okay, suppose I have a line. I have 4 operator insertions here, but the Wilson line I can always conformally transform into a circle, and then I can make it into a line again. So so this ordering 1, 2, 3, 4 actually should be equal to the ordering 4, 1, 2, 3, and that translates to this particular crossing equation which we have. And the question which people try to ask is it possible to bootstrap this equation? The question which we in particular asked is with input from the spectrum. I should mention that people, by people I mean Meneghelli, Lee and Domenech in this paper, and also Meneghelli Ferrero have tried to bootstrap this earlier and actually got very, very interesting results. However, they were able to analytically bootstrap it at strong coupling, and they had to take some input from supergravity, I believe, and also make some assumption about the HPLs that show up at each order in perturbation theory at strong coupling. Nevertheless, they have very, very, very interesting results. But our question is different. We want to do non-perturbative bootstrap, and we want to provide inject input from the spectrum. So is it possible to do this? So in the last 10 minutes, I will try to explain our attempts at trying to do this, whether it's possible to bootstrap it. So the first attempt that we did was the following. So let me just, so here to make the notation simpler later, so we just rewrite the crossing equation. I just write it as some function g of chi. And I want to divide that into a known and an unknown part. Of course, the identity and the BPS B2 behavior is known. So I just want to use this shorthand notation G1 plus B2 for the known part. And this is the unknown part. So this basically is our crossing equation. Now, the first attempt was to use a method developed by these authors, which was actually successfully used. So this kind of idea was successfully used by these authors earlier. And the way to do it is you take the unknown part of your crossing equation, you truncate at some particular state. So for example, in the plot I showed you 35 states. So you truncate at some point, you truncate at 6, 7 state. And then, so you truncate at delta n, and then you evaluate this crossing equation at n values of the cross ratio, and then you have n equations and you solve for C delta I. So then you get one set of solutions, and then you do this, I think, for many different choices of chi, and then you take average, and then you see if you can. It looks quite simple-minded, but it worked quite effectively for these people. Unfortunately, for us, it didn't work, and that was made us a bit sad. But nevertheless, we moved forward. So we had a second attempt. The second attempt is the following. So we start with studying functionals which look like this. So I have a functional which acts in the following way. It can be written as a sum of alpha L, some coefficient, times the Lth derivative acting on some function. And basically, we can act with these functionals on our crossing equation. Ideally, what I want is I want the mth, so I want the mth coefficient to act on the conformal block corresponding to the nth state to give, I want that to give me delta mn. So what this means basically is that I want my functional to give me 1 at the state whose OP coefficient I'm interested in and 0 at all other states, okay? And ideally, I want to do this because then all I need to do is invert the equation and I can calculate, I can get an expression for C square for the OP coefficient of that particular state, right? So practically, of course, I don't know the entire spectrum. And it's so what we do is we just, we have this until some point, and then beyond some point, we say, okay, let the functional just be positive. I'm sorry. Let it be small, but there's no need for it to be positive. Now, this actually works quite well. It works well, but it was hard for us to quantify the error. So we had no idea whether what we were producing was meaningful or not. So we were kind of happy, but not really. So then we made a third attempt. So now the third attempt was to use more traditional numerical bootstrap techniques, which have been developed by the Bootstrap community, so by these authors and many, many other people. So here, what we want to do is we just want to find two functionals, a plus and a minus, which, so one of them gives +1 on the state whose OP coefficient we're interested in. One of them gives -1. They are greater than 0 for all states above a particular point, after a particular point. So in this case, suppose I want to find the OP coefficient of the first insertion, so of the state corresponding to the insertion of phi parallel, then I just say alpha plus minus acting on G delta 1 equals ±1. And then from G delta 2 onwards, I keep it greater than 0. And then the game is to maximize the functional acting on the known part, okay? And when you do that, basically what you can do is you can, so what you get is that the functional acting on the known part plus C square delta for the delta you're interested in times 1, because I made it equal to 1, plus something positive is equal to 0. And this you can use basically to bound your OP coefficient. And then you optimize the parameters of your functional using the semi-definite programming package developed by Simon-Stuffin, and then you try to restrict the bounds further and further. So luckily, it worked for us. So the third attempt actually worked, and this is our result. So we managed to get a non-perturbative plot for this particular structure constant, C square phi perpendicular parallel as a function of G, which is square root of lambda over 4 pi. As you can see, it interpolates really well between the weak and strong coupling analytical bootstrap results. And the important thing is, so we managed to probe finite coupling, which is quite remarkable. The thickness of the line, which I should mention is not very thick, actually shows us the error which we have. And as we go to stronger and stronger coupling, we see the bounds become smaller and smaller. So that's good. So that actually made us very happy. And
so let me ask. So you made the thickness of this pink band, or you also this black one also have?
No, the black one. The black one is our stuff. So the thickness
how about this pink one, which looks less precise? I mean, it's also error or?
No. The pink one is just just the perturbation theory.
Perturbation theory. Okay. So
Yeah,
this width means some sort of variable.
Say again?
This width of this pink band is also some
Yeah.
sort of variable.
No. I think it's just to show. It's
Okay.
But yeah, okay. I will speak more about the error now. So as I said, attempt 3 was rather successful. Actually, before I speak, I need to make one more statement that out of the 35 states which we had in our spectrum, we actually just used 2 states and bootstrapped exactly 1 correlator, and we managed to get really, really good plots. So that's already very impressive, because usually to get such plots, you need to bootstrap multiple correlators, and it's very surprising that we had to use just 2 states. Anyway, so yeah, so just a comment on the error. So the way, so this graph shows that the error that we have at different values in G for different number of derivatives. Okay, so in this STBB thing, you need to fix the number of derivatives. So for 5 derivatives, we had quite a high error. For 45 derivatives, for example, the error started to go down. And then actually the extrapolation and number of derivatives goes to infinity is well behaved. So we were able to extrapolate to infinite derivatives and get some kind of limiting error. So what this means is that at the worst, which is around G equals a quarter, we have only about 2 digits of precision. And the another thing to see is that as the coupling becomes stronger and stronger, actually the precision becomes really strong. So at stronger coupling, we really just get a number, which is quite cool. So yes, okay, in the last 2 minutes before I conclude, I'll just mention some other experiments which we did, which was trying to find more structure constants. So the structure constants associated with the second and third state in my spectral plot. So there, what we did was we assumed that we knew C1, which I just showed you in the previous slide. And then out of the sum which we had, we took out C2 and C3, kept them as parameters, and did the same kind of thing which we did before, and tried to find inconsistent bounds in order to restrict the space. So we were able to restrict the space of allowed values of C1, V, C2 quite well, but we weren't able to resolve between C2 and, sorry, this is a plot of C2 square and C3 square. So between C2 and C3, we were able to like restrict the space of C2, V, C3, but we were not able to like resolve between C2 and C3. Nevertheless, this was just some experiments as well, which we did. Yes, so that brings me to my conclusion. So here is some food for thought. The first thing is just, it's surprising that we managed to get this result from limited spectral input. As I said, we just used 2 out of 35 states. So is there a way in which we can add more spectral information? So this is something we should think about. Is there a way to include other input from integrability? As I also mentioned earlier, can we bootstrap more correlators? Maybe that will help. Is there a way to include more correlators? That could be some way to go. Furthermore, is there a way to do this entire thing? So what we did now was numerical, but is there a way to do it analytically? Of course, at strong coupling, maybe it's possible. I mean, at strong coupling already, Meneghelli-Ferrero have some results, but is it possible also in general to see some more analytic stuff? Finally, is it possible to extend this approach for local operators in n equals 4? As I mentioned before, there is this double trace operator issue. So is there a way to understand how to bring that in? And finally, specifically because there were some recent really nice results. So recently, Alessandro, Bogdan, Kolya, Andrea managed, also Dima Wallin and Simon Ekammer, they all managed to propose some quantum spectral curve equations for ADS3 CFT2. So maybe there are some horizons there for this approach. And also is there some way to understand ADS2 CFT1? So relate in some way to some of the work which Alessandro has done with our way of looking at kind of ADS2 CFT1 as well from this defect point of view. So yeah, I will just leave you with this possible mantra, which is quantum spectral curve plus conformal bootstrap, does it mean the solution of n equals 4 Yang-Mills? Who knows? Hopefully So stay tuned. Hopefully we will have an answer soon. And thanks very much.
Thank you very much. Are there any further questions?
I think you're muted, sorry.
Sorry. So when you say that you needed only two states, so it's like number of states is like truncation level, and if you increase number of states, the results should become more precise. I suppose this is correct.
So this is what you expect, but then when we tried to do it, it didn't work. So it's a bit of a mystery why it did not work.
So I wonder if it looks promising, but at the same time that you get too good results at the small number of states may be bad thing, or I just wonder.
Well, so it's not that we get an extremely good result, right? We get a limiting result. So we are not able to reduce the error. So with this input, there is some minimal amount of error. There is some limiting amount of error, and we cannot go beyond that. So for G is equal to 1/4, I can't with two states as input, I can't get better than three digits of precision, for example. Sorry, so the reason I showed this was, you're absolutely right. So we use this state, and then we truncate. We truncate basically after this state. And so what I was trying to say was that, sorry, this is taking some time to load, but my point is that with just input from two states, it is a very surprising result, but the point is that you see here, this is a limiting error. So this is an extrapolation for the number of derivatives goes to infinity. So that means that even if I have infinite number of derivatives, there is some limit. There is some limit on the precision. So, whether this means that this particular CFT data can correspond to more than one CFT, or whether it means that there should be some other way to improve it, this we don't know yet.
Okay. And also, in general, even if you introduce all the states, you're not guaranteed that you can get zero error, but I suppose Bootstrap is always some sort of
there's no guarantee.
Yeah.
There's no guarantee. In fact, actually, even in our own thing, if we add one more state, somehow the bounds actually become worse, which is very counterintuitive. So, I think the reason is more because this STBB is kind of designed for somebody which does not know anything about you just have your crossing equation OP, and that's it, right? You don't know either the spectrum nor the structure constant. So I think because of that, if we just put in the spectrum, if we input more spectral information, somehow it gets worse. But maybe one should think a bit more and not use it like a black box, and try to extract, try to see, because intuitively you expect that if I inject more spectral information, I should be able to reduce this error at least in principle to zero. But it's surprising. This is some things which we are thinking about right now, but we don't have any concrete answers yet.
Thanks.
Further questions?
Also, when you talked about the integrability first, you're saying that the integrability is true only at one loop level, but
no. So that was just integrability is there in non-perturbatively. I just said one loop because that was easier to explain. That's
okay.
Just because I wanted to explain something.
Okay, so I just wondered if it's one loop, why in the intermediate region you could see nice agreement. But,
no. It is not just at one loop. It's everywhere.
Okay.
Okay. Well, thank you very much again.